All right. So, DART, the Double Asteroid Redirection Test. We are the first planetary defense mission for the NASA Planetary Defense Office. And just as a reminder, planetary defense, of course, is assess, search, detect, and track, characterize, plan, coordinate, and then mitigate. And DART is the first mission to do that. So, where are we now? We're still launching in June of 2021, and we're going to impact the Didymos system in 2022, in October. So Didymos is a binary. It has a moon that is Didymos B, that's about 163 meters in size, and then the Didymos A, which is the main asteroid, is about 780 meters. They're separated by about a kilometer. We're targeting Didymos B. It orbits Didymos A with about a 12-hour orbit, and our impact is going to change the orbit of Didymos B by about 8 minutes. I mean, our requirement is 73 seconds, but because our spacecraft has been growing in mass a little, and actually this is the first mission where I can say, oh, the mass is actually really good for us, right? Because it'll make it easier to observe from the ground. So we're going to impact Didymos B, and we're going to change it by about 8 minutes. And then Andy and Nancy and a lot of other scientists are going to spend a lot of time observing the change in the light curve from the ground, and hopefully we'll be able to see the shift. So that's the basic story of the mission. We've been doing this for a few years now. We are on our way to CDR, and I'll talk a little bit about that in just a minute. But first, I will point out that DART is not only it's not only a kinetic impactor demonstrator, which is what the planetary defense portion of it is, but we also are a technology demonstrator, and we're demonstrating a lot of new key technologies. So number one technology for us is, of course, is our autonomous smart nav system, which what is going to guide us into Didymos B. We don't see actually Didymos B until we're about an hour away from it, at which point the spacecraft will take over and guide us into Didymos B. So the whole time we're targeting Didymos A, and then the spacecraft will switch over and just hit Didymos B, and we'll just be watching it from the ground. We have an ability to say, oh no, you're not doing this right, abort, go here, but we're not planning to do that. The spacecraft will do it all itself. So that's the autonomous smart nav system. It's really based on a lot of the missile guidance technology that we've been doing at APL for quite a few decades. And it uses, so the other piece of DART is that we don't have a very large payload. In fact, we only have one camera, and that's a narrow angle camera, Draco, and that's what's going to be used to detect that switch and get us to Didymos B. So the other piece of it, and we heard Steve Squires talk about the Caesar mission going to, they're demonstrating NextD. Well, we're demonstrating NextD here, and we're going to be flying it first. So we've been working with GRC folks for a while to demonstrate this new thruster technology, and it's a new propulsion engine, and they are gliding quite happily along and actually building us a flight thruster at this point. So it's good. The other piece of it, we're also going to be the first ones to fly the rollout solar arrays. Ours are not as big as Caesar. We're only about 22 meters long solar arrays, but that's still pretty big. And it's a first powered flight of these arrays. They were demonstrated on the ISS previously, where they basically rolled them out and rolled them back in. We're not planning to roll them back in after we roll them out. That is not part of this mission, but we are planning to keep them and have them generate the power for the ion propulsion engine, which uses a lot of power. So then we also are demonstrating some of this, something that's called CoreSat Avionics, which is an FPGA-based system, and that's what houses a lot of our smart navigation on there. And in addition, we just signed up to also fly transformational solar arrays, which are special concentrators that are going to provide about 5 times the amount of power that the current state-of-the-art solar arrays are going to be doing. So that actually really enables some of the outer planetary missions, but we're going to be the first ones to fly. And they're part of the solar array, the rollout solar array, so we're going to be generating power there too. And in addition, so it just keeps going, right? So we also are demonstrating a new type of high gain antenna, which is a flat antenna. So DART status, I'm not going to talk very much about it, but we're basically really going towards our CDR at this point. We have had multiple subsystem CDRs. Propulsion is done. We just finished harness. You know, in a couple of weeks, we're going to do power. So we're really getting ready. We did go through quite a few changes since the last time I think you guys saw a presentation on DART. So when we started off, we were a Class D mission. Now we're Class C. That change happened right around our PDR. But what we didn't realize is that it was going to propagate through our whole system. So although in theory, not many things have changed, some things have changed. And in particular, we are no longer a rideshare and we'll have our own launch vehicle. So in addition, we added a CubeSat, which is, I'm going to talk about in just the next slide, and the transformational solar array. So our big news right now is we're in the process of acquiring our launch vehicle for DART. The selection was going to be finalized next week. However, with the government shutdown, that has been delayed. I think our new selection date is going to be in early April timeframe. There are additional Didymos observations that are being planned. I know that Andy is going to do some observations on early April. So we're going to have more observations of Didymos. And then, as I said, NextC has really started the flight production of the thruster and electronics, and that's a big deal for all of us. So let me talk a little bit about this fun new thing that DART is carrying, in addition to all of our other technology. And that's a light Italian CubeSat for imaging asteroids. It's called LITRA-Q. Our friends at the ASI are providing this really capable CubeSat. It is based on Argo Moon design, which is supposed to fly on the EM1 mission, Exploration 1 mission, which is the first flight of the SLS in 2020. That has been slipping dates. You know, they started off, I think it was, 2016, or then for a while it was 2018, 2019. Now they're out to 2020. On the happy side, though, the CubeSat has been sitting on their shelves waiting for the launch to get going. So Argo Moon is actually in a really great shape. So we are in process of solidifying the payload, but it will at least have a narrow angle camera. Argo Moon has both a narrow angle camera, I think we might have a laser instrument and a wide angle camera. We are only planning to use a narrow angle camera, but there might be another instrument on there as well. It has a variety of goals, right? So it's supposed to obtain multiple images of the DART impact ejecta flume. So it's going to, the con-ups are that about 2 days out, we release this CubeSat, and it's going to follow us in as we impact on Didymos. For a while there, we called it selfie sat because that's really what it was doing. It was just going to take a selfie of us as we were slamming into the asteroid. Because originally there was, as part of this mission, there was AIM, which was the European contribution that was actually going to do the same thing. However, that didn't come to pass. And Hera now is going to be, if selected, is going to be there a couple of years later. So this allows us to take images of the ejecta and really try to get an image of the crater that DART is going to make on the surface. But that goal is actually incredibly hard to obtain just because you can't really guarantee that you won't pass through the ejecta as you're going through when while you're trying to image the crater. So that goal might actually fall off. But definitely looking at the plume evolution, the ejecta plume evolution is one of their #1 goals. And then looking at the non-impact hemisphere as well. So they would basically follow us in about 5 minutes after, and they're supposed to have their preliminary PDR, preliminary design review in March, so in just a couple of months. So you guys have heard a lot about DART before, but I just wanted to walk you through from the engineering side what our path to terminal guidance actually is. So as you can see, we're launching. We spend most of our time in cruise and calibration. We do a flyby on the way to Didymos of a different system. And I think it's CB21 right now. However, we're looking at a new trajectory that will allow us to fly by another binary in addition to hitting the binary system. So that's going to be really great. We get a flyby basically of 4 asteroids before we impact one. Then we have about a month out, we finally see Didymos A, and we detected and start zeroing in on it. And at that point, we're not using SmartNav, we're using typical optical navigation, kind of similar to what New Horizons does in Messenger. About 2 days out, we deployed the CubeSat, basically shooting it backwards so it follows us in. And then we start looking at Didymos A, we classify the scene, then we select the right target and guide ourselves in. And then the CubeSat zooms by. DART has a lot of challenges. One of the #1 challenges, of course, is right before we hit the asteroid, we're supposed to be streaming images back to Earth, because once we hit the asteroid, 6 kilometers per second, I don't think much is happening. However, we did talk about turning off the transmitter just in case we missed, but just kidding. No, so we're supposed to get something like 50 centimeters per pixel resolution about 17 seconds out. Our goal is to still continuing to stream images and to stream, the requirement is only 1 image, but I think right now we're estimating that we can do 20 centimeters per pixel and stream those images back still by the time we hit the asteroid. So that's pretty much it. That I would keep it short.
Questions? Right here, man.
Yeah, Paul Abel, Jonathan. Great talk. I just wanted to ask a little bit more talk about the CubeSat.
Sure.
Do you know roughly how close it's going to get and what the resolution is? I didn't see it there. And
sure.
You mentioned some of the goals. I saw the narrow angle camera and the colors and things in terms of that. So any more details on the payload and what the resolution may be from the actual CubeSat itself?
Right. So they've done. Oh, yeah, I can repeat the question first. So the question Paul's asking was, I won't touch that again. So Paul is asking, what is the resolution for the narrow angle camera on the CubeSat? How close is it going to get? So what kind of resolution would they be able to get? And then whether they can do color, basically, and if there's any other payload on there that would do color, or maybe a thermal imager or anything like that. The answer to that is, right now it's all TBD. We think that we've been doing a lot of simulations with the Italian team, and we see that we can basically get within 50 to 100 kilometer flyby of the asteroid. At about 50 to 100, 50 kilometers, I think they get less than 1 meter per pixel resolution. So it's actually a surprisingly powerful camera. They're also doing autonomous guidance as well, which is kind of amazing for CubeSat. They have a dual propulsion system, also amazing for CubeSat. In terms of other payload, we don't know yet, and that's something that they've been discussing. Right now, it really is just a panchromatic black and white camera. They thought that they could do additional filters, and that's where you would get a little bit more color, but that's what we have right now. Okay.
I just checked your answer. Quick question about the spectral side. So you showed that Didymos A is a sense, but you have any constraining on the spectral side from the ground or Didymos?
I don't think so, Andy.
Question?
Which spectral type?
We have no
Yeah, no clue.
independent information.
I mean,
So it's more likely it would be S-type, right?
Yeah.
I had a couple of questions. You said that you'll only pick up Didymos B an hour out.
yes.
So are you doing the second targeting with the xenon thrusters, or do you have some other thrusters as well?
So no, we have a dual system where
Okay.
we have hydrogen thrusters and xenon. Actually, NextC is only getting us the flyby. We're not planning to use it for anything else. Our trajectory that we're investigating right now is basically a straight chemical trajectory that would take us to Didymos B even if NextC doesn't work. So NextC would allow us to go off and do the flyby and then come back to our primary trajectory, which is to hit Didymos B.
Ah,
Yeah, so we're just using the hydrogen thrusters for that. And they're firing autonomously.
other questions?
Someone was typing.
So, one last, any chance on the flyby target that will be a human exploration mission setting? In the NAS list?
I don't know. I'm going to check on the website that Paul showed. Yeah, we can check. Yeah, we have some information of this additional target that we're going to be looking at. It's 1994
AW1.
AW1, which is there've been some observations on. Go ahead, Andy.
Yeah, if you're willing to say what it is, you're the one that said what it is. The possible flyby target is 1994 AW1, which is, I think was the first binary discovered from the ground, the first one proven from the ground, and it's a lot like Didymos in its kind of qualitative properties. So it's an S-type with about a 800-meter primary and a few 100-meter secondary.
Yeah, but we're still investigating that trajectory. Right now it's CB21, which I think is the single asteroid.
One question online, will Argo Moon fly by as well or go orbit?
So Argo Moon actually just, it is just a flyby, and it just stays with us the whole way to Didymos, and then we just release it only 2 days out. So usually the CubeSats are released as soon as the launch vehicle comes off. That's not going to be the case for Didymos, for Argo Moon Leachy Cube. We're going to keep it really close, keep it nice and warm.
So, what delta-v does that 8-minute change in period correspond to?
What delta-v?
Repeat the question.
Oh, sorry.
Oh, Andy.
Go ahead, Andy. Andy's very excited. Go ahead, Andy.
I don't know things. A fraction of a millimeter per second.
And that's the change in,
I usually never deal with questions because I know that.
yeah.
That is the change in the linear speed of Didymos B around Didymos A.
Okay, so the change in linear speed of Didymos B around Didymos A as a result of the impact is a few millimeters,
A fraction
Yeah.
of a millimeter.
a fraction of a millimeter per second.
Yeah, very little.
But the orbital speed is tens of centimeters a second. So it accrues very quickly.
But the orbital speed is tens of centimeters per second, so it accrues quickly.
Yeah.
All right, thank you very much.
Sure.
Okay, and so